As I say, I have a few slides of a project that I worked on with Jim in 1983, and it spilled over into 1984, as most projects tend to do. They grow in time, or they creep. So the participants at the time with Jim, UC Berkeley, and of course now retired. Myself, at the time I was at the University of Auckland in New Zealand, now at University of Nevada in Reno. And Mehmet Chalabi was involved in the summer of '83 on this project, USGS. So the scope of the project was to conduct shake table experiments on the performance of base-isolated, single-span, skewed bridges funded by the National Science Foundation. And we were interested in both the in-phase and the out-of-phase response of this isolated bridge deck. The total number of configurations was of the order of 20, with about 10 ground motions. And if any of you have worked in isolated structures, I'll just quote Don Clyde. He said they never die. Right? You can't fail them, so you just go on and on and on and do more and more experiments and more runs with the table. It's not like a reinforced concrete structure where you're yielding and eventually you have a degraded stiffness and the like. But isolated structures, whether they be buildings or bridges, are robust, resilient, whatever the current buzzword is. We were using elastomeric isolators with and without lead cores for the energy dissipation. And interestingly enough, these isolators had dowed connections to the structure above and, of course, the floor, the table below. They were shear-only connections because we were concerned that if you had a bolted connection, you would place the elastomer into tension under strong or lateral displacement. So that means these isolators could transfer shear but not take moment into the foundations, which means that you could roll them over. If you drove them hard enough, you could make them unstable and they would fall over. And we did that. The configurations included, of course, no skew, a hybrid skew where one end was skewed and the other end was not, and a full skew. And these sketches on the right here show sort of general configurations. And for the in-phase work, 4 isolators and the full support of the bridge was sitting on the table. And for out-of-phase work, 2 of the bearings were on the table and 2 of the bearings off the table. So it's about a half scale, 20-foot long girder, 8-foot wide, 2 girders, weighing about 4 kips, a concrete deck slab, another 16 kips, and then we added lead weights for similitude reasons of another 75 kips, for a total weight up around that 100,000 pound limit. That it's a 50-ton table. So we were just right on 95,000 pounds of bridge, including the lead similitude mass. And the stiffness of the 4 elastomeric isolators at 50% strain, at a little under 5 kips per inch. So the isolated period of this bridge was right on 2 seconds. So these are some sections through the bridge on the left, the cross-section, the 2 girders, the concrete slab, and the lead above that. And underneath the isolators were load cells, so every isolator sat on its own load cell. And a plan and sections through the isolator on the right. They're about 8 inches tall, 8 inches square, almost cubes. And the hole in the center was, and some bearings had lead, and other cases was unfilled. Plan view for the in-phase work on the left and for the out-of-phase work on the right. It was possible to place the bearings into different configurations so you had different skews, as you could see on the left. So this was the model pretty much late on a Friday afternoon. This was in summer of '83. I recall it quite clearly. We'd finished assembling the model and home for the weekend. By the time we came back on Monday morning, it had collapsed. This is the first model I ever worked on, then and since, where the structure failed under its own weight. So here it is on the floor, on the floor of the table, where it's come down off the isolators. And as it's come down, it was originally straight on the table, it has come down and rotated, skewed across the table. So on the right, I think it's me lifting the lead pallets off the bridge deck, and standing or talking to, I think it was Pat Quinn, I'm a technician at the time, standing on the right. Notice none of us are wearing hard hats, no safety equipment, but this is taking the collapsed bridge apart, taking the lead off the model, and to do the forensic work. So what had happened, lesson number one, was that these isolators had been cold vulcanized together, not hot vulcanized. So the bonding between the layers and the internal steel shims was inadequate. And under sustained load, it crept and came apart. So this is one of them here. And you can see the isolator now vertical, but is turning apart like a sandwich, like layers of rubber that have peeled off the steel shims because of the adhesion due to cold vulcanization. But we went with the cold vulcanized bearings because they were tremendously cheaper than working with a fully bonded, fully hot vulcanized bearing. So this led to an immediate requirement in the AASHTO isolation guide specification that all isolators shall sustain an axial load for at least 24 hours prior to being delivered to the bridge. It's been relaxed in recent years because this was a significant cost item, but it stemmed from this experience in summer of '83. So this put a wrinkle into the schedule, and it was now a matter of getting another set of bearings through a set of suppliers in Texas and put the bridge back together. So the replacement isolators were obtained, and it was not until December of '83 that we started actually doing the tests on the bridge. So this is putting it back together again. This is a view of the 45-degree skew out-of-phase experiment, where there are two bearings on the table supporting, and two bearings off the table supporting the other end of the bridge model. Because the bearings were not bolted into place, they were shear only, and therefore no moment connection, it was possible to roll them out. And frequently we would do that, and we had learnt by now to in fact put, I'll say 2x4s, probably temporary wooden supports to catch the bridge should the isolators fail. And so what you see here is the bearing is now on its side. It's come off its load cell to the left, and it's now on its side, and the bridge has dropped down on it, and is partly also supported on the safety systems. Since then, of course, the industry has moved to having confidence that these devices can in fact take some tension and they're bolted into place, and you don't see isolators shear-only connections today. But we learned from these experiments how to, in fact, do the equilibrium equations and how to design against rollover if you have to have a shear-only connection. And then finally, there are these sets of photographs here, of these sets of slides. Okay, this is Jim at his best, wanting to demonstrate visually to anybody who would watch or anybody in the lab at the time of the acceleration reduction that he mentioned just a few minutes ago. So a glass of wine was placed on the lower flange of the bridge superstructure, and another glass of wine on the shake table below, and of course the isolator in the background. And then the table run, and you can see that the wine is spilt on the table in copious amounts, but the wine glass sitting on the bridge model itself is intact. It didn't topple over and it didn't spill its contents. So just visually you could see that the accelerations feeding the glass of wine on the table were much higher, enough to slosh wine out of the glass, whereas that of the table itself, that of the bridge itself, was safe. This is my slide, second to last slide. So here are some, this is filming a video was taken of the wine glass experiment and was used by many people promoting isolation at the time because it was so obviously beneficial to, in fact, change the dynamics of the bridge deck. So we have the videographer on the floor of the lab, and we have Jim, I believe it's Jim, instructing the camera person down there. The person to our left, I believe, is Chris Arnold.
Yeah, that's right.
Chris?
Yeah.
I'm not sure, but this could be Ivo in here, and I'm not sure who the others are. But if you've got a sharp eye, there's the bottle of wine. This all got finished in February of '84. So the conclusions: avoid cold vulcanized bearings just to save money. In every case, the limit state was rollover, and bolted connections would eliminate this, and that's pretty much the standard practice today. And we found that the isolated bridges are not sensitive to skew like a conventional bridge is, and not sensitive to out-of-phase motions like conventional bridges. So a tremendous amount of information came out of all these runs that have influenced the profession, particularly the isolation of bridges today. So thank you very much.